podcast is because of a very important film that was created by Walt Johnson. It was his mission that he wanted to bring some Socratic questioning into all of the things that we hear regarding the narrative out there regarding climate change. And so, hence, he created a climate conversation movie, and you can watch that for free at climateconversation.com. I'm so pleased to have on the podcast with me Dave O'Rourke. He's the spokesperson for a climate conversation, and Dr. Richard Geyer and Walt Johnson. And so, Dave, why don't you take it from here?
Thank you, Kim. And thank you, everyone, for sharing this time with us. I think it's going to be time well spent. This is the fourth in a series of podcasts in support of the movie A Climate Conversation. You can view these other podcasts there, and we encourage you to do that. We think we've been laying down some pretty good podcasts here and encouraging conversation, which is the purpose of the documentary, fostering an honest dialogue on the subject of climate change, its causes, its impacts, and a science-based cost-benefit analysis of its potential solutions. So our podcast seeks an audience of open-minded people on the premise that neither entrenched group on the left or the right is willing or even able to change their views, and the 80% of the American citizens that fall in the middle should take control of this economically, socially, politically, and culturally vital conversation. And today we're, as Kim mentioned, lucky to have a couple of great guests. So let me first introduce Dr. Richard Geyer, Doctor of Engineering, Senior Research Physicist, and a Senior Instructor in Physics at the University of Colorado. Richard is also President of Electromagnetics Incorporated. He's a specialist in thru-the-earth magnetics, among many fields of study. I just love this thru-the-earth idea. He's the author of dozens of publications, and as you're about to learn, a man of many interests. Walter E. Johnson, who's become a friend, is a respected geophysicist, a certified geologist, and a registered professional engineer who earned his degree from the Colorado School of Mines. Walt has written and published more than 20 papers and publications in his area of expertise, which includes high resolution and shear wave seismology, inversion, and direct detection techniques. In 2022, he personally funded, wrote, and produced A Climate Conversation. The documentary film, as I mentioned, seeks to foster a transparent and inclusive approach to the topic of climate change. This podcast will cover one of the most important subjects in the climate debate, the impact on the environment, which fits into the general topic of costs and benefits of the potential solutions and those proposed. There's been little consideration of both the costs and the benefits amid the general hysteria of climate crisis that surrounds this entire topic. In the film, which again we encourage you to watch, Ken Gregory of the Friends of Science presented his analysis of the dollar costs of conversion to net zero, which yielded a staggering result, over $100 trillion. And it turns out from some more recent research, that may be a low estimate, but there are other costs, and they may be equally dramatic. So what we want to talk about today, the impacts on the environment and the externalities and the impacts of those externalities on a hungry planet. Specifically, we want to look at the entire supply chain of solar energy, and we'll be covering some topics I'm confident you will not have heard discussed before. So having said all that, and I know that was a lot, why don't we have both Richard and Walt tell us a little bit about their journey and how they got here and about this podcast today.
Richard, you go first.
Okay, well, thank you. Actually, Walt and I have similar backgrounds, both in geology and geophysics. I also graduated from Colorado School of Mines with my PhD there in geophysics, and we know similar people. He graduated a little bit earlier than me, and I was involved in both exploration and research for petroleum and minerals companies. And I realize that the standard of living of the United States, as it is right now, depends on these minerals and petroleum. So we are very similar, and I did work at, I even taught at Colorado School of Mines for a while as a research associate before I joined Gulf Minerals, now owned by Chevron. And also I worked for Marathon Minerals too, International, and Marathon's Research Lab in Littleton, Colorado. So I've had a lot of experience in geophysics, and after that I went to National Institute of Standards and Technology in Boulder, and I was in electromagnetic fields division. My background in geophysics was actually electromagnetic techniques for remote sensing. So I was adaptable to go into higher frequency things and things that might relate even to the grid or to things that would affect in a negative way the grid, like, for example, high altitude electromagnetic pulse or other things, that would actually take our grid down, even an unreliable source of energy that we're going to be talking about today. So we have similar backgrounds, quite a bit. We have similar friends, and we just discovered it kind of, between the two of us. And so I did work at NIST, and I do have several hundred publications, 3 best paper awards there, and both in IEEE as well as in material sciences. And I have had some exposure to semiconductors too that are used in photovoltaic array, solar arrays. So kind of a broad spectrum of experience, and with that, I'll let it be up to Walt now.
Like Richard, my background is in geophysics also, but I'm a dirty geophysicist. I get my hands in the dirt. I specialized in seismic. I specialized in exploring for things. I've been all over the world exploring, which has been fun for me. About 20 some years ago, I founded Exploration Geoconsultants. It's a geophysical supply company to help people find things and solve problems. So that's where I've been mostly. And in my tour to get here, I had been uncomfortable with the way our society was looking at a lot of things. And that's what prompted me. In fact, I was driven, very, very much driven to make the movie. That was a mission for me. And as a result of that, this is kind of a fallout. I've run into Richard, and a bell went off when I first listened to his talk about the hazards of solar panels and some of them. And in our talks earlier, we had Dr. Patrick Moore on here, and I had asked him on the earlier podcast, what did they do for an environmental impact statement before they built the wind farm offshore Nantucket? And he said, well, everyone knows the whales migrate through there, but nobody sat down and made a detailed look into what happens here. And as a result, we've killed off about 10% of an endangered species, the right whale. So there are a number of things, and a bell went off here. We are not looking at what we're doing with green energy as far as the environment. And that's kind of the crux of Richard's talk that got me started. So that's good. So let's get on to what you were doing.
Sure. Should we look at the first slide?
Okay, go ahead. We'll just have...
We've already introduced ourselves, but this is really a short synopsis of some toxicity issues that I was asked to talk about at a conference we had recently in December in Lakewood, Colorado. And although I'm not a toxologist and I'm not I'm not a toxologist per se, but I can recognize what some of the toxic issues are relative to the use of some semiconductors. They're fairly well known, actually, and published. And I'm not a horticulturalist. You're going to see I'm going to be talking a little bit about some things in horticulture with regard to agricultural plants and crops that we have. Should there be something that was very negative and that would happen in terms of the destruction of solar panels. And the first slide, though, I really have is to compare the principal energy sources and energy densities. Energy densities are very fundamental. We see there's different, when we look at any discussion of energy, people are using different units. It's kind of, what should I say, pain in the neck, but it's the way it is in the United States. They have not standardized standard international units, so people talk in terms of different units that they're familiar with. For petroleum, petroleum provides for a 42-gallon barrel, 6.12 billion joules, or if you're familiar with kilowatt hours in your electric power bill, it'd be 1,700 kilowatt hours, or in terms of British thermal units, another unit. I used to teach energy and the environment at the University of Colorado in Denver, as Walter said, for 12 years. So I was familiar with this, and most of my students actually were environmental scientists. So if you look at a British thermal unit and you don't remember exactly what that is, well, the amount of energy that it takes to heat 1 pound of water by 1 degree Fahrenheit. So depending on the units that you're looking at, it's a regardless, you're comparing different materials used for electrical power generation from a different source. And you'll notice here that we don't even see solar, we don't even see wind turbines because they're so small. We'll get into that. Petroleum, for example, 142-gallon barrel provides 5.8 million BTUs. That's a lot. Bituminous coal, how about 26.6 million for 1 ton? Not a metric ton, but 2,000 pounds. Natural gas, on the other end, for 1,000 cubic feet, 10 by 10 by 10 at standard atmospheric pressure would be 1 million BTUs. Gasoline is a comparison. 1 gallon is 125,000. And uranium is probably has the highest energy density of 25 million for 1 gram. Remember, 1 gram is 454 grams in 1 pound. So when you're talking about sources of energy, you're talking about how much and what does it produce. So we could go on to the next slide. There's vast amounts of coal in the United States. There are greater than 300 years. The United States is, you could look at the United States as really the Saudi Arabia of coal. There's vast amounts of natural gas, petroleum. The supply is that supply of coal, gas, and petroleum is about 86% of all the energy used in the United States. There are other sources that people have heard about, geothermal, there's hydroelectric. Hydroelectric for renewable is probably the most efficient because basically the potential energy all goes into kinetic energy that drives a turbine, in an electric power plant. Wind turbines are the most inefficient. Solar, which has less wind turbines and solar in terms of energy sources and used in the United States, are less than 1%. And there's reasons for that. They're costly. They have much less efficiency, and and they're toxic nanoparticles in solar. But in the manufacture and disposal, they're toxic. And we're going to talk about that as well as references to it. Nuclear has the highest energy density. It's the least expensive, but there are issues on some of the radioactive byproducts, for example, plutonium, if you have a fission plant. Let's go to the next slide. If you look at energy used in the United States, it's a lot. We're a very advanced country, and I put down 1,000 trillion BTU. What's a trillion? Well, it's a trillion is 1,000 billions. So here we got 1,000,000 billion BTUs in 1 year, or for one quadrillion British thermal unit, and the U.S. uses about 100 quadrillion British thermal units per year. That's a lot of energy, but it is a large technical society that satisfies our standard of living. And if you looked at the use breakdown, about 39% of that is used by electric utilities, 27% in transportation, 22% in industrial use, and 11.6 or 12% for residential and commercial. So this is talking about the energy use. Forms of energy, well, we got electrical energy, people are used to that. We get batteries where charge is brought to a higher potential or voltage that permits lighting, electric motors, computers that we're using right now, television, air conditioning in our homes or businesses. And where we have a conversion, we can always have conversions of one type of energy into another. Like a battery is chemical energy and it's converted to electrical energy, where you can have mechanical energy turned into electrical energy in generators. Generators also can convert electrical energy back to mechanical energy if you use them as motors. So there's different forms of energy. You always have conservation of energy, and you have waste of energy, even when you don't get all the energy that you want out, and it turns into thermal energy, which you may not be able to use. Let's go to the next slide. So forms of energy, I won't dwell on this. For solar panels, it's electromagnetic radiation, and it covers a wide variety of phenomena, typically from very short wavelengths, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays that you're familiar with if you go to a medical doctor or a hospital. And when you're talking about forms of for solar panels, you're typically talking the optical spectrum. They're electromagnetic waves, and actually they can extend out to the invisible part, infrared, but mostly it's visible light. Most of the solar spectrum of our sun is in the visible region. So we can go on to the next slide. Next slide. Now, in one example of heat generation from chemical energy as a result of burning coal, why are we burning coal in the first place? We're burning it to create the steam, the water that actually drives a turbine. At an electric power plant, and that's based magnets that are rotating within the armature that create current flow in the electrical grid. And when we're burning coal, I simplified it to coal is made mostly just plain carbon. It can have other components too that we have to be aware of. And if you combine it with oxygen, it forms carbon dioxide and releases, if you wanted to know how much energy does that release? Well, 95 kilocalories, that's 1,000 calories. A little calorie is, like a full calorie per mole. I'm not going to go into we don't have to go into all the details, but 1 mole is a gram molecular weight. So you can actually relate this to the periodic table in terms of the atomic weights and how much coal you use to provide how much energy. Going down to the bottom, I put note that carbon dioxide is used in photosynthesis. That takes place in all agriculture, plants, trees, and at the same time, they release oxygen that all mammals breathe, including us, all warm-blooded animals. In oceanic waters, it should be remembered too that carbon dioxide, when it goes into solution, it forms weak carbonic acid. And weak carbonic acid is basically like the fizz in your pop cans. But it's a weak acid, and because it's a weak acid, one must be careful and monitor, whether reefs might bleach. So that's a valid issue, in the environment. But basically, the carbonic acid typically forms, at warm temperatures, and with calcium in the oceanic waters, it forms lime, or under burial, it forms limestone, which is in all the geology books back to the 60s. And Walt knows about that too. And limestones are 25% of the sedimentary rocks. So when we're talking about carbon dioxide formation from the burning of coal, the carbon dioxide is used by the trees and the plants and the agriculture in photosynthesis. And those trees and plants actually produce oxygen that we breathe. And so actually it's kind of a symbiotic relationship. Carbon dioxide we need if we want to have any kind of plant life. You take carbon dioxide out, you'll have a barren desert. But the trees and the plants actually release oxygen that we breathe, which we definitely want. We don't want to go down to zero carbon. Yeah, that would be very, very, mankind would cease to exist. So carbon dioxide forms, and in ocean waters, it forms limestone. Maybe next slide. If we look at what it does in terms of agriculture, the food we eat, the metabolism of sugar, sucrose in our bodies, if we're looking at what happens with the plants, the carbon dioxide in the sunlight plus the carbon dioxide plus a temperature range between 75 and 86 degrees, which is a normal growing season, the plants and agriculture, trees, grasses, they form carbohydrates. Carbohydrate chemistry can be quite complicated, but here's an example that if we, in our own bodies, if we're using glucose in our own bodies and combine that with oxygen, it produces carbon dioxide, which we release ourselves. So human beings, mammals, all release carbon dioxide that is used by the trees and the grasses and the agriculture. And that's what I've got down in the bottom, that, that it's just kind of a symbiotic relationship that we have. They release the oxygen. We breathe out carbon dioxide ourselves in terms of normal metabolism, which they use. So it's highly how energy is used in the United States. This is dated from 20 years ago. But it hasn't changed too much in the United States. The electric utility is about 39%, transportation 27%, industry 22%, and residential and commercial. That was on a previous slide. And I put down in red that it's highly improbable that wind turbines that have fiberglass blades, actually a derivative of hydrocarbons and petroleum, because of their lightweight and their strength, and solar panel farms that use semiconductors can even come close to supplying the electrical energy needs, even with the use of lithium-ion storage batteries. And it's important for people to realize, too, that lithium-ion storage batteries are also environmentally toxic hazards for disposal. They're very toxic. They do have high charge, but if you short them, it's explosive. And lithium is also considered a toxic material for disposal. And it's a good question for somebody to ask, where are the lithium-ion batteries being disposed of? Are they being disposed of in landfills? They shouldn't be. That is an environmental issue. Cost considerations support this. Even though NREL, National Renewable Energy Labs in Boulder, projects a $350 billion solar industry by 2035. The highest efficiency for renewable electrical energy sources is obtained actually with hydroelectric power plants. In the United States, hydroelectric, they contribute about 300 billion kilowatt hours per year for the past 30 years. They provide actually 30% of all the electrical energy from renewable sources. And that comes from the U.S. Energy Administration. So it's always important to ask, where does this information come from? Is it a reliable source of information? Can you trust it? But the recent issue for hydroelectric, for renewables, is that a number of them have been eliminated and returned, actually by President Biden, to indigenous peoples. and they're the most efficient when it comes to renewable, if you're talking about efficiencies. Maybe next slide. Next slide. So for energy resources, for residential, commercial, it is natural gas. For industry, coal, natural gas, and petroleum. Transportation, almost all petroleum. More recently, we've had some electric battery input, but it's still mostly all petroleum. Some natural gas, especially in Europe, is used in transportation. They carry it in their trunk, so it's efficient, very efficient. Current effort is to use electric vehicles, but are they really safe? That should be asked by people, because they do have explosive, and actually the vehicles are very heavy because they anchor them in steel. So, and another thing that people should realize with electric vehicles is when it gets very cold, like when I say 15 degrees Fahrenheit or less, they lose their charge far more rapidly than does a normal lead acid battery, which is recyclable. Lithium-ion batteries are not recyclable. So if you're looking at toxic materials, I'll choose and you're environmentalist, I'll choose a lead acid battery. Pay the fees. The lead can be reprocessed. Use aprons for X-rays. You know, lead can be reprocessed, and so can the sulfuric acid. Lithium-ion batteries cannot be. So for electric utilities, when I say that lithium-ion batteries could be dangerous, that's only if they're shorted. But can they be shorted? Automobile accidents, yes. Are they non-toxic for disposal? No, they're not non-toxic for disposal. That's important to recognize. For electric utilities, still in the United States today, including in the state of Colorado, 50% coal. We're the Saudi Arabia of coal. We have got a lot of inexpensive near-surface coal. 20% actually is nuclear, 18% natural gas, 7% hydroelectric, 3% petroleum. Now, if you add all that, 50% plus 20, 70, 88, 95, 98, 95%, we don't see anything at all in terms of energy resources presently being used that are needed in terms of solar and also in terms of wind turbines. That's because they don't provide much that is reliable that you can count on. In the United States, not in China or India, which are the largest users, coal is particularly being taken out as a source of energy. And I personally believe that's a big mistake because it provides, coal. When you burn coal and create carbon dioxide, it doesn't sit there. It is taken out by photosynthesis in the plants and agricultural products. So there are some valid reasons, such as that you can have coal that produces ash, but in the United States, we've got scrubbers. In China, Mexico, India, very few scrubbers. So there are things with coal that are negative, but in the United States, our environmental protection regulations take account of a lot of that. There can be methyl mercury content or ash content, like I say. But when coal was used as a water heat source for driving it's used as a heat source for driving electric turbines. Another reason is the production of carbon dioxide as a warming greenhouse when coal was burned. But when you start talking about carbon dioxide again, it's taken out of the atmosphere. And so you produce it, but it's being used. It's being used in photosynthesis. It's a very fundamental thing that most people learn at far younger age than I am. So it's noteworthy that utilities have been given also $100 billion to phase out coal plants and to replace them with very large solar panel farms over a significant part of the United States agricultural lands. That's important. United States is one of the biggest food producers in the world. And it would not be in the interest of the United States to lose the agricultural production that they have by replacing them with large solar arrays whose economic or environmental impact hasn't been looked at and considered. Bottom, I've got carbon dioxide is a greenhouse gas. Yes, it is, but isn't there not a natural process of carbon dioxide removal that I've just been talking about that's beneficial for Yes, that's what I've been saying. It is. There by photosynthesis. And again, simple terms, carbon dioxide plus water plus sunlight. And that's actually the blue and the visible blue and the red part of the sun spectrum. That's what, and it is temperature line, just like you would think. During the regular growing season, 76 degrees, about 86, that's the normal growing season. Forms carbohydrates. And there's a lot of carbohydrates. The chemistry is complex, but in general, it forms carbohydrates plus water plus oxygen that we breathe. So photosynthesis, again, produces oxygen that all mammals breathe. And down the bottom, I said it is complex, and it also requires chlorophyll. And you have the absorption of the red and the blue light parts of the sunlight, and what you're seeing reflected is a green color in the chlorophyll itself. Go to the next slide. So ideal conditions for photosynthesis and plant growth exist for 400 parts per million of carbon dioxide. And I think Walter discussed this earlier in one of his podcasts, where it exists for 400 parts per million of carbon dioxide in the atmosphere at 76 degrees. That's our growing season. Below 180 parts per million of carbon dioxide, it's not good. Plant life, you can ask a horticulturalist, plant life cannot exist, and no photosynthesis will take place. And that's a very important point. So we need at least 180 parts per million of carbon dioxide, or plant life will not exist, including all agriculture. Now, how does the history of atmospheric carbon dioxide, how do we determine that? And I think this also Walt talked about in a previous webinar or podcast. It can be determined from ice cores and direct measurements. And so you can actually see how much carbon dioxide average, how it has increased from back in the 1700s to what it is presently. And back in around 1750, right before the Revolution in the United States, American Revolutionary War, it seems to be that it was about, from measurements, scientific measurements, about 280 parts per million, and has come up to about 400 ppm today, or last year, 2023. So, and if we're looking at an estimate of carbon dioxide flux from fossil fuels, you could also consider, well, what about deforestation? Land use. You will have a higher carbon dioxide, local accumulation of carbon dioxide in the air, just due to land use. So if you're talking about a global warming agent, just due to land use, if you have carbon dioxide, that you should consider that. So, and then things become less uncertain too, because you've cut down all the trees. A city like Los Angeles, hardly any trees. Take all the trees and cut them all down. Or it would be important, and with the Amazon, if you cut all the trees down, that's true. You're taking out the trees that are actually using the carbon dioxide and giving off oxygen in return. So until 1920, deforestation actually contributed more than anything else. Actually, it was deforestation that contributed more carbon dioxide. And then how much? about 1 billion metric tons, 2,200 pounds, until deforestation actually contributed more carbon dioxide than anything else. So next slide. And some of the references that I would give, one is the top one there is 2015. It's by Eric Runkel. He's a professor in floriculture or horticultural extension specialist in Michigan State University in the Department of Horticulture. It's a land grant university, just like Colorado State University is. And he's a well-known publisher in the horticultural area or floriculture extension. Moore and Bracewell actually looked at in terms of lifetime of excess carbon dioxide and published things on that in terms of global biochemical cycles. And that's 1994. So a person can look up these papers and actually read it. It just doesn't stay there. That we're all going to drown in carbon dioxide and die. I mean,
If I can inject something,
sure.
the U.S. corn crop creates as much oxygen as does the Amazon rainforest in a year.
That's amazing. That's good. That's amazing. Thank you, Walter. Thank you. So if you're looking now at questions specifically on electrical energy and solar sources, or IPV, this photovoltaic materials, where do almost all high voltage transformers where do almost all of them come from that enable electrical energy to be delivered to distant sources? Well, we're talking now a little bit of physics here. And this is a concern by the power grid people, by power engineers, because you need these high voltage transformers, and they have to be supplied with, they enable electrical energy to be delivered to distant sites, and they come off from People's Republic of China. Well, in addition to that, the semiconductors that are used in solar voltaic arrays also come from People's Republic of China. And incidentally, one of the largest companies of most advanced semiconductors actually comes from Taiwan Semiconductor. So there's a great personal interest China, People's Republic of China, would have in both delivering electrical energy transformers that enable relaying electrical energy from one state to distant states, or even for making semiconductors that are used in solar arrays. There's a big...
Richard, just a quick question.
Yes. So
What is China doing? I hear that they're ramping up their coal production.
That's true.
Are they doing much in this solar and wind arena, even though they are manufacturing so many of the solar panels?
They sell them to the United States.
Yeah, but they're not using them.
Not much.
Okay.
No, actually, they are ramping up coal very much. In fact, I believe, Walter, I think it's like for every 2 weeks, there's a giant new coal plant.
that's about right. 2 a month is what I
Two a month. In fact, China will probably is willing to buy all the coal the United States will produce. And because of that, they produce far more carbon dioxide, even regardless of where you stand on this. They produce 4 times more than the United States does. And so whatever your thoughts are, it won't even matter because of atmospheric mixing. China produces far more than the United States. If you look at graphical plots, what the United States is producing in carbon dioxide, it's a very small amount compared to what China and India and even Mexico produce. And they don't have the environmental protections either. They don't have ice control. Look at Beijing. They don't even have the environmental things, but they're using much more coal. And there's probably there's good reasons. It's energy density. So, and yes, they are ramping up and like 2 months. So it almost brings to bear that does it for people to say, well, the United States, that they don't take these steps. Whatever the United States says, it doesn't almost matter what the United States says, because China is producing so much more carbon dioxide than what the U.S. does. And we'll get in later on that when it comes to other gases that people perceive are negatively, like methane, that also is destroyed in the atmosphere. But we'll talk about that a little bit later. So what will happen? And I put down here questions in black with answers, what I perceive as an answer. You can see that in red. What will happen if planned solar panel farms with existing technology occupy vast agricultural lands? Well, it's pretty clear that lower production and more expensive, and the food will be more expensive. We've had a lot of inflation already. Devaluation of the dollar, basically. But this will even increase food even more. Right? Cost of food more. Because you have lower production. Therefore, it's going to be more expensive on the market. And there'll be other costs too of natural forces of nature. This is a big one. This is a big environmental thing. If natural forces of nature destroy solar panels, that will require testing and environmental remediation, if it is even possible, because they could turn into Superfund sites. Wow. And that's what we're going to talk about. So maybe next slide. So here I ask, these are kind of rhetorical questions that one might ask, or Walter or Kim, you could ask too. Are there any potential problems related to toxicity of semiconductors used in solar arrays or solar cells? And you have many solar cells in a solar panel. You could say that because they're encapsulated in silica, that if there's no inclement weather or hostile weather, maybe not. They may not produce much energy, have the energy density of some of the others, like coal and natural gas. But there is a problem if hostile weather, which includes hailstorms, tornadoes, even hurricanes, if they destroy solar panels, because there's toxic materials. There's layers of toxic materials. And there is a possibility then that you could have toxicities introduced into soils, near surface soils and water, by plant osmosis. We all know the kind of, in a simple-minded way, you water your plants and in your house and put in water, put them in the sunlight, of course, and there's chlorophyll there and they grow, and you can poison them by putting toxic materials in your soil, deliberately poison them. Well, you don't typically think of maybe a solar array as being toxic, but they have been tested. It's not as though that they haven't been tested. Many materials have been examined by toxologists and botanists for toxicity, including some that are used in solar panels. And some of these have been published. Actually, they're in the open literature for people to read at the National Institutes of Health and Environmental Protection Agency as well, where some of these materials that are toxic have been looked at. One of the largest environmental impacts from solar energy systems would come in both the manufacture as well as the eventual disposal. Photovoltaics, photovoltaics or solar cells, they require a host of harmful materials in their construction. That is why where they're made, typically they're made in clean rooms where people are with white gowns, they cannot be exposed to the things that they are come in the process of making these semiconducting films that are used in solar cells. So even if you have benign silicon, it can be doped with arsenic too. arsenic. People know arsenic is toxic, are known for many years, and other toxins. His solar cell panels were destroyed. This is a point. If they are destroyed in hostile weather conditions, hailstorms, tornadoes, hurricanes, and there's basically, or crushed, if they're non-usable anymore, you can get any particulates, and those resulting particulates can cause toxic pollution in soils, and could enter the food chain, could plant osmosis. Just like whatever you have in your household solar plant, if you water it, if you put toxic materials in that, that's going to come up to that plant and probably kill it. Or at least, but if it's a plant that you wind up eating, corn crops, fruits, grapefruit, then it could get into the human body or other animal bodies. So for massive solar panels that are installed over large agricultural lands, that could be a very, very serious issue for a number of reasons, not only the environmental impact for people who are environmental. We're talking environmentalism here. We support the petroleum industry in terms of what it produces, but if you have an oil spill, typically an oil spill, for example, will disappear in the near surface cells. It's eaten by microbes, but this is not the case with heavy metals. It stays in the cells. So there's a big difference. If you have an oil spill out in the oceans, that can do damage, but mainly to the sea life on the top. The ducks, the geese, anything that goes up, that does damage, but on land, petroleum really doesn't, it doesn't last very long. It's naturally taken up. That is not true with heavy metals or say semiconductors. With that last point I wanted to make, Kim, on the previous slide, the industry manufacturing processes, they do contend with serious pollution issues. I want to just emphasize, despite it has a high-tech reputation and it uses clean rooms, but those rooms are filled with toxic materials, and you have to be very well protected against those toxic materials that are put on those solar cells. They're very toxic. All right, maybe next slide now.
Just to comment on that, we talk about the battle of the narrative all the time. And here, what you've just described is something that's called a clean room, which is actually very toxic.
Yeah,
And
that's
so
why
it's really
people are
toxic.
totally covered when they're going into a clean room. They have different classes too. There's different class, class 1, class 2, class 3, class 5, but it's very dangerous, and you dare not go into them when they're making them, because if you inhale any of those gases, and they're in gaseous form, and when they deposit them on a substrate, it could lead to all types of, not least of which is bone cancer.
Wow. Okay.
And heart edema. There are many things that have been, because they're toxic. Here, I've just got a review of, and this is a little bit dated. The efficiencies might be a little bit larger, but not too much. Different types of solar cells. And there's reference to this too, because whenever people see information presented, they should ask, where did you get that? How reliable is it? How accurately was it measured? It's very important. That's what they do at NIST, right? The standards for accuracy for measurements. That's what I used to do, but when you're looking at cell technology and you're looking at the efficiencies, that efficiency basically relates to how much of the energy's light, which consists of photons in this region from visible blue to the light blue is higher frequency versus red and lower frequency end of the visible spectrum. How much is that is turned directly into electric energy? It's direct current, just as a side. So an electrical engineer, power engineer would say, well, we're not using direct current in our devices. We're using alternating current. So you have to have inverters. You have to have inverters to convert direct current to alternating current. But if we're looking at the efficiency, we're really talking about how much of the sunlight, the energy of the sun, is actually converted into direct electrical energy. You know, with a direct process instead of burning coal to heat water to drive a turbine. So in a power plant. So here, if you're looking at single crystal silicon, that was one of the earlier, it was about 14 to 17%. If we go up now, you know, you can look down the scale and you can see, well, concentrated with silicon, these are different elements. But if you're going down now to the second to the last, the cadmium telluride, 7 to 9%, that's optimal. And actually, they've done some improvements on that, or they will claim we get up to close to 20%. I've seen graphs from National Renewable Energy Lab. But there's another issue. You're going to have to keep them cool. So some of that electrical energy, you're going to put back in cooling the actual solar array itself. So you're not going to get it all in electrical energy. That is why not only they are considered unreliable because they're not available in the evening hours or when it's a cloudy day, where we have natural gas will provide that, coal will provide that, but not solar. The storms that we had here in Colorado the last few days, you would get zero from your solar array on your rooftop.
If I could interject something, notice your next to last material there. North of town here, they manufactured plutonium triggers for the nuclear bombs.
Yes.
And the plutonium and cadmium with it infected an area, and that's a Superfund site now.
It is.
Mostly from the plutonium, but the cadmium also is involved in that.
That's true, Walter.
And the only way they spent a lot of time looking, what do we do now? They closed down the Roxy Flat plant, and they discovered that the cheapest way to handle it would be to cover it with dirt and leave it alone. Nobody can go in there and dig in the dirt. You can't go dig in the dirt there. But it's a park, sort of, but it's a Superfund site.
However, as you know, when they were building the road around there, they discovered some of it. They had radioactive, they had Geiger counter sensors, so they repositioned the road. Left it there. And also I happen to know a person who worked there as a machinist, and he has bone cancer right now.
Sure.
So
Dr.
Geyer, another question. You said that these have to be cooled. So is water involved in the cooling process?
It can be, yes. It can be, I come from the Mojave Desert. Maybe you don't need, maybe you can just use water, right, as a coolant, and not something like antifreeze. What I'm saying, something that would freeze. Yes, that's all I'm saying. But in summertime, when you have direct sunlight overhead, probably you could use water, but that's going to take some of the energy away. And when you do that, and if you don't do that, and you just let your solar panel, for one thing, you get optimum efficiency always when the panel is perpendicular to the sun's rays, just like you would, yes. So it's high noon during the summertime. However, high noon during the summertime, that array, that panel can heat up. And when it heats up, it can heat up to 200 degrees Celsius. 100 degrees Celsius is boiling point of water. 200 degrees Celsius is double the boiling point. The efficiency drops down to 5%. So if people are selling solar arrays, you really should qualify it with the people. I'm saying, well, wait a minute, it's not going to be that optimal 20% all the time. It's only going to be that 20% at a fixed time of day, not in the early morning hours, not in the late hours, or also when the solar panel heats up. It'll drop down. And that's been measured by National Renewable Energy Lab.
Good.
By Dr. Al Sandana, who was a personal friend, and it could be circumstantial, but he died of bone cancer I don't know whether he was exposed or not. I can't say, but he was a personal friend of mine. And he was the associate director at Enron, Elson Darnell. So anyway, going back to this, solar efficiencies are maximum. This is what I said, when you're vertically incident on the panel. But panels usually, if you really wanted to get the best efficiency, which is not anywhere close to the energy density of what we've been talking about, but it would be to keep them perpendicular to the sun rays. But you always get this thermal heating. And at higher expected temperatures, 200 Celsius would be the high point, double the boiling point of water. They get hot in the summer time, unless you, of course, use some of the energy to cool them. And efficiencies can drop to 5% compared to what they were at a measured between 20 and 25 Celsius. That's what they are typically standard measurements at the National Renewable Energy Laboratory. They will give you efficiencies at that temperature. Right. But they also did measure at higher temperatures. But this is the one that they give measurements to, that they standardize to. So people have to ask those questions, what are the conditions? People need to be aware of them. People need to be educated. I really believe that. Local warming effects with very widespread use. If you have solar arrays all over large agricultural areas, they can alter the Earth's natural net energy balance. That affects climate. So some have questioned whether that could be comparable or even carbon dioxide as a warming gas.
Wow.
And we're talking now 55 million acres of federal land.
It's incredible.
Going to that.
Yeah, and Walter was talking about federal land. What about private land that the utilities have been giving some funding for, I believe by an executive order by President Biden, and they have a certain number of years to lease land. And then I've heard even to take land by eminent domain, but I don't know whether that's legal. I question the legality of that. And if you do that, you're decreasing agriculture. You got the possibility of toxicity if you have harsh weather. Do they have tornadoes, for example? What's the occurrence of tornadoes in southeastern Colorado, close to Kansas? Do they get tornadoes? Yes, they do. What about hailstorms? Southern Michigan, southern Illinois, where it's cloudy half the time. How much solar energy are they going to get when it's cloudy? What about Wyoming? What about South Dakota and North Dakota? Right now, the utilities have been giving funding to lease land up, and I believe that they get a tax credit if they do it by a certain time of private lands, private agricultural lands. So not only will this decrease food, but you've also introduced another thing about how much energy does this really provide, and what are the toxicity issues. So here, this slide goes into toxicity of cadmium telluride. Walt talked about it relative to rocky flats, which is true. And cadmium telluride and cadmium sulfide are used in second generation. What are second generation? Well, they'll be referred to by the National Renewable Energy Lab. Well, they're some of the most economic. They're less expensive, but the toxicities are similar to the elements, cadmium and tellurium. You can look at toxicity of the element, the periodic table, cadmium and tellurium, or even their compounds, and you can even find it in the European Water Framework Directive. It's not just in the United States, but you can find it even at NIH or in places like Denmark. Cadmium is listed as a priority hazardous substance in the European Water Framework Directive. I would tell people, don't trust everything I say, look it up. Could I go back to that other one, Kim, just for 1 second? It's listed, and they give what is toxic. They want to keep the amount of cadmium released to less than 3 millionths of a gram, 454 grams in 1 pound. This is 3 millionths of 1 gram in a liter being about a quart. The U.S. Environmental Protection Agency, they set a maximum of a contaminant level for cadmium on these second generations, solar arrays, 5 micrograms per liter. Denmark has a most stringent, and that's about a half of a microgram per about a liter. Very small. It's very toxic. So we should be aware of that and be concerned about it. And not necessarily say the sky is falling, but look at the conditions where it could be very toxic and be very harmful to the people of the country. All right, maybe next slide, Bob. Go ahead. So toxic effects, I mentioned these things. These things can be looked up, and of course they don't test this on human beings, but they can test it on mice, rabbits. It has been tested. There have been tests made, and mostly it's evident in organs like liver, kidneys, placentas of women, brain, lungs, and bones. Symptoms, a lot of symptoms a doctor could say that who's experienced with toxology, he would ask, have you been exposed to this? And some of them, they might have, I realize you can have abdominal cramps for other reasons and nausea for other reasons, but this is also a symptom for a toxic effect if somebody has been exposed to this. And in the more extreme case, you have eye exposure, death, pulmonary edema with effects of emphysema, bronchiolitis, and alveolitis, and clinical conditions are cardiac failure, and including bone cancer, osteoporosis, and even cataract formation. Although we know other things can cause cataract formation too. And references for this. There are some references. It's always important to look at what are the references and how, what the merits of the different references, how much you can trust them. How do they measure? What are their accuracies? The International Journal of Environmental Research, Public Health in 2020, volume 17, number 7, talks about toxic metal implications of agricultural soils and animals and human health. So you can look that up. A person could look that up. Another one could look up very easily was a PhD thesis in the University of Witwatersrand in South Africa. And that is listed on the following place on the website. It's an essay. This was also, it'll be on NIH, the National Institutes of Health, where they were talking about heavy metal toxicology, including cadmium, including tellurium, and the compounds, which comprise second generation solar arrays. So we need to be concerned with that, especially if they're destroyed. Some constituents here, the World Economic Forum, have not considered measured solar constants that can change. Walter knows this as a geologist and geophysicist, and so do I, where the sun's radiation doesn't just stay the same. It varies as a function of time, over geologic time. And that can be far more significant before we were even using coal. And Walter, I believe, has already noted that, in a previous podcast with you, Kim, where you've had changes in the climate, changes in temperature that have nothing at all to do with any use of any petroleum, any natural gas, any coal. It was a geologic thing by our changes in our sun's output. And if you look at books and good books in climatology, and I've got some I can freely give, there have been increases of temperature, naturally occurring increases of temperature, followed by very rapid or very slow, it's an asymmetric curve, very slow cooling areas. And these cooling areas are known by climatologists. So people need to be familiar with that and not ignore it. Sometimes they don't know about it. But for example, in the 1600s, there was a modeling or modern minimum that when the Pilgrims came over to the United States, what did they come over for? They came over maybe for political reasons, you know, from Europe. But when they came over, a lot of them starved to death until the Indians told them how to grow meat because of the temperatures. In Boston, ice and snow, middle of the summer, modern minimum. Now there are cycles of our sun. Don't ignore them. 200 years later, there seem to be 11-year cycles and 200-year cycles. If you talk with a solar physicist, they're known. I think they should be speaking more about this. The 1800s, that was a time when there was wet, cold weather in Ireland. Remember when all, and a lot of Irish people died from starvation, lack of food. But the potato blight, that's when they came to the U.S. Wasn't much better. But they came to the U.S. at that time. And so these were caused by solar cycles. And that one was called the John Dalton minimum. John Dalton was the father of American chemistry. You know, and John Dalton actually was a chemist who could meticulous records of temperature in his time. And so here these are solar cycles that can have warming and cooling characteristics, and very significant ones. And you also, people have heard about, well, if you have a volcanic explosion like Mount Helens, Mount St. Helens, and what about the one Krakatoa? You know, producing ash into the far more than CO2 and ash content in our atmosphere than we would ever even think of, that warmed, that cooled the temperatures down significantly. Not by any use of petroleum, not by any use of coal, not by any use of natural gas. So in this regard, going back here, I said the World Economic Forum. We've heard this talk too, and I've actually heard it on the media. I won't. Maybe I should say by whom, but he's a well-known person. They have measured solar constants that they've not considered them that can change, as well as other factors that are important for any global climate or global temperature change. They need to. They should. Otherwise, it's not being properly represented. In this regard, there's even been some in the World Economic Forum that have proposed release of aluminum flak in the Earth's upper atmosphere. So that would reduce, hypothesized, carbon dioxide global temperature increase. I say hypothesized because the carbon dioxide is being used, but they're attributing the carbon dioxide as a warming glass that's causing it. So let's put aluminum flak in the upper atmosphere. That if you did that, you would poison. That would be an environmental catastrophe over agricultural lands. Furthermore, NASA, our own NASA, National Aeronautics Space Administration, they monitor global temperatures with satellites. You can look up their monitoring. They've been doing it for over 10 years. And they've monitored what is the composition of the atmosphere. It's still 80% nitrogen, 19.2% oxygen. Good for us. That's what we need. It's exactly, not more or less, for Homo sapiens. And what's the other 0.8%? I said 80% nitrogen, 19.2. Well, that's 99.2. What's the other 0.8%? Heavy inert gases that don't react with anything. So, and it hasn't changed. It hasn't changed. So if the World Economic Forum had were saying that we ought to do this to reduce global temperatures, to reflect the sunlight, if you will, from carbon dioxide, which doesn't even stay in the atmosphere, it's used in photosynthesis. This would cause an irrevocable soil contamination and loss of productive, irrevocable. And aluminum is another EPA toxic material. On top of that, we're part of these groups that are espousing to get rid of all hydrocarbons. It's completely contradictory. Maybe go to the next slide. So here, I think that this was on the original batch of PowerPoints that I sent to Walt, and he suggested that I not talk too much about it. But this, I did some evaluation. I listened to National Renewable Energy Lab. What are they doing in research? And basically, what we're at now is a second generation. I'll leave it at that. The cadmium telluride. That's where we are. They're less efficient. They're lower cost. People are looking at other types of semiconductors, photovoltaics, but again, they're not producing much, and you must use it. You have to consider the toxicities. And most of the semiconductors that you have, they are used with the rare earths, and the rare earths dominantly come from China. So I'll stop here. I'm sorry if I took too much of your time. So
Fascinating.
Well, that's a nice setup. Thank you.
okay.
Because we've talked about earlier that we are not applying the same standards for environmental protection of green energy that we do for any other kind of energy. That's a hazard.
Yes.
And we ultimately will have to start dealing with that as a society.
Walter is right, because recently the Northwest Research Institute, I think they're based in Oregon, has stated that 90% of all unusable solar and lithium-ion batteries are put in landfills in the state of California.
And I checked that with Ronald Stein, who's in our movie and wrote the book, Clean Energy Exploitation. He says exactly the same thing, that these are all hazardous and no one is paying any attention. They just dump them.
Walter's right. And then I've understood too, even some of the lithium-ion batteries are dumped out in oceanic waters. I've also heard from an attorney to a senator, Terry Griffiths, that a lot of the toxic materials are being taken to places like Virgin Islands and Haiti. It's really pretty sad, that the destroyed panels are being taken there, for the people, and left there. But in Northwest Research Institute, which is a good institute, they did evaluation. 90% of the solar panels are unusable, are being put into landfills. That's future Superfund sites. Probably we'll hear about it. And that comes in a state which claims to be one of the greenest, if you will, and purest and most concerned about the environment. Well, that doesn't go along with that statement.
Can I thank you for this wonderful presentation. I'm sure I learned a lot. I'm sure everyone watching this has learned a lot. But what strikes me is the only number that I hear coming out of places like the World Economic Forum or the UN or the Intergovernmental Panel or what have you is a measure of degrees centigrade or Fahrenheit that could happen by the end of this century. What you don't hear is a dollar value put on this. This is going to cost the earth. Some people say Miami will be underwater, or despite certain notable politicians buying waterfront property in places like Martha's Vineyard, you don't hear a number that says this is going to be $7 trillion of damage done to the earth because of greenhouse gas emissions. You don't hear that number. That number's not mentioned, or I've not heard it. And yet, and we saw an article this week from Bjorn Lomborg, who continues, in my opinion, to do fantastic work and advocacy, and he says that some of the most popular climate policies and other proposed solutions actually will have costs that are far greater than the cost of climate change itself. And I'm fascinated by that. So we're talking about hard dollars. You're talking about human costs, people dying of hunger, people being poisoned, the earth being poisoned. So the ironies are very rich here. But I saw also in the Lomborg article that the according to World Scientific, going to net zero worldwide would cost. So we had Walt in the film. We had the wonderful research by Ken Gregory showing, over $100 trillion to go to net zero. Going worldwide would average $27 trillion a year for the rest of the century, reaching 60 trillion in the year 2100. Can we talk a little bit about why we don't? How can we engage a conversation about sense, dollars and cents as well as common sense? How can we get people to understand how much $27 trillion is? It actually turns out to be 5 to 6% of global GDP. And now you're talking about the death of 1 billion people. So what happens next? How can we get a conversation going about dollar cost and dollar benefit of the problem, such as it is, and these proposed solutions?
Well, I've always thought very simply is more education, and people being forthright and willing to say things that they know. And can back them up with actual concrete data and measured data, like anybody in a measurement lab would have to do. Tell me what the exact accuracies are of your measurement. What are the uncertainties? And but the education is a very big thing. I find I've discovered, in my opinion, all across the spectrum. I think some of these things should be taught in grade school almost, or for sure in high school, and let alone college. I believe classes. I believe this. I always, when I taught University of Colorado and I taught energy and environment for 12 years, I thought this should be a required class. Not for me, not that I would be the sole instructor, but that I thought it was very important for them to be able to distinguish between what's weed and what's trees and things like that. So I really and I believe it should be not an elective. I think it should be a required curriculum for young people throughout, so that people can question things properly and know what to look at, know what the terminology is, and not be mystified by it. I really believe that. Education is a very big thing.
Well, thank you for the work that you have done and are doing. So I'm fascinated by everything, Kim. This is really your show. But the one thing I know is true is, if you do ask an alarmist, for lack of a friendlier term, so why are greenhouse gases bad? And they'll say, well, it's fires, floods, storms, people dying. But we know that deaths related to climate have dropped 97% in the last century. 97% reduction, from 500,000 people to about 15,000 people a year die, and mostly they freeze to death. There's a handful of people who die in a hurricane or what have you, unfortunately in a forest fire. But a more successful world is a safer one. And that more successful world is associated with the use of fossil fuels for their energy density, their availability, and their relative non-toxicity, not to mention how economically valuable they are. This time with you, for me, it's just been invaluable. I'm so glad you were here with us today. Walt, as always, you're just the best.
It's part of you.
We want that second movie, Walt, and we want to encourage everyone watching this. You're probably already on the website. If you haven't been, please go and encourage others to visit, to watch the film, and start to have conversations that can put policy downstream from science instead of the way it's been trending now for most of my life. So, Kim, that's what I've got here. It's all you.
Well, I have learned so much, and I thank you, Dave. First of all, you really encapsulated everything that we heard. So well done on that. Dr. Geyer, you and I've known each other for a number of years, and I knew you were a really smart guy, but now I know you're a really, really smart guy.
Oh, thank you.
And Walt Johnson, I don't even have the words to say regarding your vision, to see how important it is to have these conversations. And because ultimately we want to be good stewards of our earth, and we want humans to thrive and flourish. And I thank you and your wife, Ramey, for stepping up to the plate, your vision on this film, A Climate Conversation. Again, you can watch it for free by going to aclimateconversation.com. But Walt Johnson, I thank you.
And thank you for both of you and Dave, because I've gotten a lot of feedback from people that will watch the film on the website, but they go along and they follow all the podcasts in detail. And these are serious people looking at this. And I'm pleased with the kind of people we're attracting here. Thank you to both of you.
Thank you. Thank you very much.
Fantastic.
Well, until next time, again, Dr. Geyer, Walt, Dave, thank you.
Thank you, Kim.
Thanks, Kim. Just Richard. Fine.